Okay, so this was your guys' homework problem on this kind of like newer topic of accumulation. So I feel bad, you guys, that we didn't have our Saturday study session because we would have had a whole like entire Saturday study session for an hour and 15 minutes on accumulation. And these are definitely problems that I would have been doing during that time. But now it's just something that you're going to have to try and learn from watching the videos. So it is a newer thing that they seem to test a lot now on the AP exam because it's more like, do you really understand? Do you actually have the concepts? Do you understand the calculus? Or are you just like mimicking some things like this? You can't just mimic your way through. So this was back from 2015. It is number 1, so that means it's calculator active. So if you are doing derivatives and evaluating derivative out of a number, you're math eating it. You could definitely use y of something to just plug a number into a rule. And you definitely are thinking, oh, if I'm integrating something, I math 9 it, if it's a definite integral, right? Calculator active problem. So you'll need a calculator a ton for this. So as we read through the sum of the problem, I've already written some of the important information up on the board, but let's like read it and understand why I wrote what I wrote. So number 1 says, the rate at which rainwater flows into a drain pipe is modeled by the function r, where r of t is equal to 20 times sine of t squared over 35. So you definitely want to, when you put that into your calculator, probably put it in y1, right? It's the first rule you read, so you're going to store it in y1 and write that down, that that's where you're storing it. And use your pretty print so you get your fraction vertically up and down. And you have to be in radian mode since we have trig going on. This is where some of you get so confused. You don't like read the units. So if it says that this is the rate, first of all, it uses the word rate, at which the water is flowing in. Notice I labeled it as flowing into the drain pipe. And it says cubic feet per hour. Even though this doesn't have a prime on it, this is a derivative. It is something with respect to time. So if you write your units on the side, I think that will help you realize like, oh, this is a rate of change. This is a derivative of the volume of the water, right? If it's cubic feet per hour, it's the derivative of what would be going on if we like integrated and we just went back to cubic feet. That would be like the volume of the water coming in. So then we have in the next sentence, oh, it does tell us our time is from 0 to 8 hours. I wrote it in closed bracket interval notation instead of 0 is less than or equal to t, which is less than or equal to 8 hours. And then it says the pipe is partially blocked, allowing water to drain out from the other end. So this was my draining out rule. And it says d of t, probably for draining out, right, equals negative 0.04 t cubed plus 0.4 t squared plus 0.96 t. Make sure you catch the t on the end of that. And that's cubic feet per hour. So this is another derivative that is about the rate that the water's going out. And I'm going to store that in y2. And again, I know it's a derivative, not because they didn't put the prime on there, and you don't slap a prime on there all of a sudden. It can just denote a derivative as a regular function, but I know it because of the units. It's cubic feet per hour. And it's on the same time frame. So it's like, this is why we call this accumulation, right? It's accumulation when you have stuff coming in, or you have a rate in and a rate out. So you have these derivatives and you have stuff coming in a rate of change and stuff going out in a rate of change. And if you want to get to your final amount, you're going to have to consider both of them. And the stuff coming in and stuff going out is for the same time frame from 0 to 8. And then the very last sentence, of course, we can't just like miss and skim over. It says there are 30 cubic feet of water in the pipe at time 0. So I kind of already marked this and I have 0, 30, but you have to like, again, notice the units. This is just cubic feet of water. So this isn't about r of t, and this isn't about d of t, because those are rates. This isn't about the amount at my time of 0, where I just have the cubic feet of water, the amount of water in the pipe at that initial time frame. Okay? So this is a part A, B, C, D. And because it's part A, B, C, D, if you don't get a part, it's not going to kill you out of the 9. It's probably pretty evenly distributed. You guys have already done this on homework, so look back at your homework and see what you did in your own notebook on it, and see how your notation goes, and see how it compares to my notation, and then how the points are awarded. So part A says, how many cubic feet of rainwater flow into the pipe during the 8-hour time interval? 0 is less than or equal to t, which is less than or equal to 8. So they often will do this on accumulation problem, where they'll ask you a question that only deals with one of them, right? It says, how many cubic feet of rainwater flow into the pipe? So we don't care about the stuff that's draining out. Don't we just want the stuff that's flowing in? And we want it for the whole time interval. And remember, it's calculator active, so we're going to get points for our setup and our answer. So don't we want to integrate the cubic feet per hour from 0 to 8 of our flowing in stuff, r of t, with respect to time. So even though I wrote down y1 and y2, that was for my own like benefit, I can't put y1 here because that's calculator notation and not calculus notation.
But in your calculator, you should have something like that.
Yep. And then you should get approximately 76.570. And I don't know, was that exactly 0 or did it round up to 70, Mr. Herney?
It's 76.570. And then there's more decimals.
Okay. Cubic feet flow in on our time frame from 0 to 8 hours. So they didn't ask for units, but we've been trying to say this with some of the problems that we did last week as well. I would practice the units right now because I think that this year's exam is going to be a lot about units and do you really understand? So if you're practicing those units, I think it's going to make you better and better and better as you prepare for your test on May 12th. Okay? So that's all we need to do for part A. So like I said, make sure that you have both of these in there, stored in Y1, stored in Y2, and just realize that the rates that you have stored in. On an accumulation problem, this is a pretty typical question. I'm not saying it's going to be there every time and every problem, but it's pretty typical. So part B says, is the amount of water in the pipe increasing or decreasing at time t equals 3 hours? Give a reason for your answer. So because if you're trying to find when something is increasing or decreasing, isn't that like analyzing the derivative, right? Like when we answer for a derivative answer, we would say, oh, this is when this amount, if the derivative is positive, is increasing at a rate of at this time. Or we would say, this is where this stuff, whatever the stuff is decreasing if the rate is negative at this time, right? So if I have stuff coming in and stuff going out, and I want to see whether or not at time 3, the amount of water in the pipe is increasing or decreasing, why don't I compare the rate in and the rate out at time 3 and see? Right? Like compare them. So there's more than one way to do this problem. This is the way I like. I like to compare them. So I would go, okay, if I want to know the flowing in at time 3, the rate that water flows in at time 3, don't I want to do R of 3? And since we've established that this is R and they told us that in the stem of the problem, we could just write down R of 3. And on your calculator, you're going to do Y1 of 3. And then I want to compare that to the draining out. What's going on with the cubic feet per hour at time 3 when it's draining out. And again, because this is stored in Y2, you can just do Y2 of 3, alpha trace on a home screen and get those values. So it looks like Y1 of 3 is approximately 5.086. Remember, if they don't specify otherwise, you're going to 3 places. And then it looks like that other part, even though I have lots of decimals, came out to be exactly 5.4. But again, we've talked about this with EVT. They're not going to assume you know which is bigger or which is smaller. So is it R of 3 smaller or less than D of 3? And if you needed to think about it in words, this was the stuff that was flowing in. This was the rate that stuff was draining out. So if our stuff flowing in was smaller than our stuff draining out, then wouldn't the amount of water be decreasing at this particular time? So therefore, the amount of water in cubic feet would be decreasing at time t equals 3. I do have to restate the time because that's not what's happening all the time. So the other way to approach this problem, and whichever way makes the most sense in your head, is you could do the idea of, okay, if I have water flowing in and water flowing out, when I want to take the water flowing in, subtract the water flowing out, and analyze it that way. But I would want to analyze it right at time 3. So if you did D of 3, or R of 3, pardon me, minus D of 3, I got that answer to be approximately negative 0.313632. I just wrote down probably more digits. And then if this is negative, that final, taking both rates into account, is a negative rate of change, then what did that mean? The amount of water in cubic feet would be decreasing at time 3. So they would take either one. I like the comparison way because to me that seems easier to wrap my head around. oh, if I have that stuff that's flowing in being smaller than the stuff draining out, that would give me the stuff draining out to be bigger, so therefore the amount of water would be decreasing at that moment in time. Okay? So pretty typical problem on an accumulation problem. Part C. Speaking of EVT, at what time between 0 is less than or equal to t, which is less than or equal to 8, is the amount of water in the pipe at a minimum? Because that means the minimum value, but you're only finding the time where you reach that minimum value. That means absolute global minimum. Justify your answer. This is an EVT problem. But in order to do EVT, we know we need our candidates, and then we have to test them, right? So I know a lot of you are going to be like, okay, well, we got to use the endpoints, so time 0 and time 8. And I'm trying to do this the same way we do it every single time, where we write it down every single time. But then you're going to need where the derivative equals 0. But you have two derivatives going on. You have stuff flowing in, and then you have this stuff going out. So it's sort of confusing. But again, with the whole accumulation, the idea, if you have stuff coming in and stuff going out, then for your derivative of the total amount of water, a prime of t, wouldn't you have to consider the rate in minus the stuff that's draining out? And think about where this equals 0, because you have both rates to consider. So in order to do that, this is going to be kind of crazy calculator stuff. And again, if we had a pure Saturday study session, this would be a lot more smooth, because you would have had a pure hour and 15, hour and a half session on it. But remember, if I have this stored in Y1 and this stored in Y2, then how about in Y3, I do Y1 minus Y2 and go back and turn off Y1 and Y2. So you're only going to be graphing Y3 at the end. So we can find all the times where we would equal 0. So we would have the other critical points, right? And if we're looking for a minimum, we also want where we switch from negative to positive. So not only equal 0, but where a prime of t changes from negative to positive. Because then that would at least be a local min, and we're trying to find the absolute min. So do you want to show them the window, Mr. Herney?
Yep.
If you didn't set up a window, oh my goodness, you guys, they're telling you the time. They're telling you the x's. It's 0 to 8 going by ones. I made my window negative 5 to 5 for the y's going by ones because I thought, well, I want to find where the x-intercept is, or the time is equal to 0. So that I've considered the rate in and the rate out, and where that derivative equals 0 for a prime of t. So I just did negative 5 to 5 because I didn't need to see much above or below. So going back to the graph that Mr. Herney showed you, it does only have one time frame, and you are switching the correct way from a negative to a positive on the first derivative. So Mr. Herney, will you do second and calc and find that for us? And remember, this is going to be an intermediate step, so we don't want to round to 3 places here, because that could throw off our final answers when we test the candidates. So it ends up being 3.2716584. At least that's what my calculator shows. Some of you that have a thinner color calculator that charges, it might have a few less decimals right here on the end, but it would have enough that it wouldn't throw anything off, because it at least carries at like 5 or 6 places. So it looks like we have 3 spots to test. So now aren't we ready to test? But in order to test, we need kind of like this general rule. Because don't we want to plug in to find the amount of just regular cubic feet of water? So you guys, I like to use A of t because it makes me think of, oh, it's accumulation, I'm finding the amount of stuff. Well, don't I need to take my initial amount at time 0, and don't I want to add, this is that twist on fundamental theorem, or you could do it Mr. Herney's way, and don't I want to add this time frame for my lower boundary to whatever time frame I want at the end to match my upper boundary? And this gets really tricky with notation and with the letters. So I don't know, I mean, I'll try to explain it, but you can't have this letter match the letters down here, is the point. Because wouldn't this be replacing those letters if we were using fundamental theorem of calculus part 1? But we know, like, we have to go, will it be the rate in, I'm going to do R of x, minus the water draining out in cubic feet per hour, minus d of x. And all of that we would integrate with respect to x, but really we'd be like replacing these with t's later on. So it's just like kind of weird with that notation, and I don't know how to say it really like a whole lot better. I think they're fairly lenient. Like if you had all T's there, but you like understood you had to do the rate in minus the rate out, and that's what you were integrating, I think they would totally give it to you. I think they just go, oh, if you turn your head like this, that T looks like an X, or if you turn your head like this, that X looks like a T. I think they're fairly nice. So remember, we have 3 to test, right? So if I test at time 0, well, at time 0, we already knew that amount, because that was the amount in cubic feet of water at time 0, which they gave us as the initial amount, which was 30 cubic feet. So if I did my other endpoint at time 8, wouldn't I be taking the initial amount, 30, plus the integral from 0 to 8, but now I want to consider both of them, of r of x minus d of x minus capital D of x with respect to x. Sorry, I'm like doing so bad with my notation right there. Or there, if I think you put t's, it wouldn't matter because you have a number up there instead of t as a letter and these letters being x's like we had over here. So you are going to just do 30 plus and then math 8 that. Remember, r for the rate coming in of the water flowing in was stored in y1. That's why you identify so you don't do them backwards. And the water draining out was in y2. And we get 48.544. So this answer is approximately 48. I was going to say 44. 48.544. There's the 44. Cubic feet. Remember, we're looking for absolute min, the time where we reach the absolute min. So right now, this one is smaller than the other endpoint. Okay, so final time to try. Find the amount where not only did the derivative a prime of t equal 0, where we did rate in minus rate out equals 0, but also where we switched the right way from negative to positive, because this local min might be the absolute one. So 3.2716584, or maybe you define this. You can't just use t there because we got other t's going on. So maybe you would change it to like, I don't know, a, probably not a because I'm using capital A for amount. I don't know. Pick a letter that has nothing to do with this problem, right? Pick K or H for Hernie. So that amount would equal our initial amount, 30, plus the accumulation that we get from 0 to that time frame, 3.2716584, of the rate coming in, r of x minus d of x, for the water draining out. Because if we accumulate that cubic feet per time in a certain time frame, we would just get cubic feet, and we end up getting approximately, for this one, 27.965 cubic feet. Does that seem right, Mr. Hernie?
Yep.
Okay. So remember, once you've tested all your candidates with EBT, which is what they're expecting to see, that you do the candidates test, you still have to do a conclusion, because they're not going to know you know which one is answering at what time is the amount of the water in the pipe at a minimum. So we actually just need to state the time that it happens at. We don't need to state the minimum value, although you ended up finding it. If it says what is the absolute minimum, or what is the minimum amount of water in the pipe, then you would state the y value. I did just state the time frame because that's all they were asking me for. So I say, therefore, the time, the amount of water in the pipe is at a minimum is t equals 3.2716584 hours. Or maybe there you go ahead and route to 3 places for that final piece, which would be okay because you haven't introduced any other or intermediate rounding otherwise. So since I'm kind of out of space on the board, I'm going to go through the points for these 3 for A, B, and C, and then we'll talk about part D. I could probably fit it. I'm going to fit it. I'm coming up here. I lied.
Don't do it.
I'm doing it. Okay, so part D has a whole lot of words, but you actually don't need to do a whole lot of work. So it says, the pipe can hold 50 cubic feet of water before overflowing. Okay. 4 times greater than 8, t is greater than 8, so that would be the open interval, parenthesis 8 up to, let's say, infinity. Water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. So we still have, like, even past time 8, water flowing in, same rule, water flowing out, same rule, but we know it will overflow once it reaches 50 cubic feet of water. Write, but do not solve, so you're just representing something, an equation, so an equation has to have a left-hand side and right-hand side and an equal sign separating the two, involving one or more integrals that gives the time w when the pipe will begin to overflow. So it's kind of like, what? But if you know that the pipe's going to overflow at 50 and you're trying to find the time when it's going to reach 50, wouldn't one side of your equation have to be 50? So I would say, okay, 50, and that's the cubic feet of water that I want to reach, and then things overflow after that, right? So this is about cubic feet of water. That's about my amount. Oh, well, we wrote something in general about the amount. The amount according to any time, where did I put that? Amount according to any time equals, the initial amount. So wasn't our initial amount of water in the pipe 30 plus, we'd have to accumulate 0, because this is the initial time, 0, to match up with the amount of water at time 0. And then it says at time W, because we don't know when this time would happen. So the upper boundary would be W. And then don't we still need to go, what would be the stuff coming in minus the stuff going out? And I'm using, again, X's because this is representing a time. I don't know. Maybe they could be times. Who knows? I don't know for sure. But it couldn't be W's there. It has to be a different letter. So, and then that's the equation that we would solve for and eventually solve for W for the time on the upper boundary. It just says to write it. You don't actually have to solve anything. So that's it for part D. You could split them up. That's why I said one or more integrals, and do 0 to W of just R of X or R of T dt minus 0 to W of just D of X dx or D of T dt, and have them each piece, because calculus is beautiful, in their own anti-differentiation definite integral and subtract in between them. But since we've done every other part, this like rate in, rate out together, why not keep them together? So now I'm going to go through the points because now we're done with the whole thing. Okay, so our 9 points this time. Part A was 2. So your first point on part A was your integrand. So did you know you had to integrate R of T dt? You don't even need to have the boundaries right. You just had to know that you had to integrate this. And that was because it was just about the water flowing in and not the water flowing out from time 0 to 8. And then the second point was your answer, because if your boundaries are wrong, your answer is wrong. So did you get 76.570 by doing math 9 on your calculator? Okay, part B is also 2 points. So you got a point for considering R of 3 and D of 3. You could have considered them, like I did, individually, and then comparing them. Or remember, you could have got over here and thought, well, R of 3 minus D of 3, at time 3, this is the rate coming in. At time 3, this is the rate going out. I'm going to subtract them and see whether I get a positive or a negative value. If I get a positive, then I know the amount of water is increasing at that time. If I get a negative, I know the amount of water is decreasing at that time. Or consider them individually and compare them. So first point is that you considered those two individually. And then the second point was your answer, which would have had to been that the amount of water was decreasing at time 3. With reason. So your reason, you guys, is more of, like, did you compare? Like how I said, R of 3 is less than D of 3. Or did you get that this was negative and then come up with your conclusion? So just 2 points on part B. Part C is EBT, and usually EBT is 3. I've seen it only be 2, and I've seen it be 4, but typically it's 3. This one is a normal problem, that's 3. So the way that the 3 points broke down was that you got 1 point that you considered this. That you knew that the derivative equaling 0 and changing from negative to positive would have had to been the derivative for the amount according to the time, which is really just the rate in minus the rate out. Did you get that you had to consider rate in and rate out together, and that you had to subtract? Okay. Then the next one after that one is that you got your candidates tests going on. So did you justify with your candidates test? So did you run through them all? Did you know that the initial amount was 30 cubic feet? Did you do the endpoint at 8, consider the initial with that, and then did you pick your other time, which ended up being that 3.2716584, and try your candidates with that one? If you were attempting it, even if you were doing it wrong, I bet that they would give you that point, because the last point then is going to be your answer. So the only way that this answer is going to be right is if you ran it on the right rule. So your answer would be that the absolute min happens, because they didn't ask us for the minimum, just for the time when it happened, at 3.27, and if you round it up, 3.272 hours, or you kept all the digits. And then part D then is 2 points. So you got 1 point for this integral, but you knew it would have to be from 0 to w, and that you had to consider rate in minus rate out. And then the other point was that you wrote an equation, so you had the one side equal to 50, and you also considered the 30, which was your initial amount. So it was 2, 2, 3, and 2 for part D. Okay? Mr. Herney, last minute thoughts?
Looks great.
Sorry with that whole like confusing part about X's and T's. I don't know. It's just weird. It's hard.